Okay, welcome back everybody to the last talk of the morning session. We're extremely pleased to have Sarah Selkirk from the Universiteit Klagenfurt, which Christian would have said better than I can. She'll be talking about from Kreweras to Gessel, a walk through patterns in the quarter plane. Thank you.
Thank you very much. So I've seen Kreweras and Gessel both mentioned in the context of algebraic combinatorics here. So I'm going to now make sure that they're both mentioned in the entire acronym. So I will be speaking a little bit about formal power series. Mainly bijective stuff following on from Eric and Wenchi this morning, but I'm more or less in formal power series. So thank you very much, firstly, for the opportunity to be here. And then also I'll just say that this is perhaps the most fun conference that I've ever attended, which is really community-oriented and trying to create things which initiate interactions. And this is really great. So I'd also like to thank the community for making it this way. So I'm not going to assume anyone really knows much about this, so I'm just going to start from the basics. And so what is a walk in the quarter plane? Well, we have some step set. It can be anything. We just have an example over here. And we draw a lattice path. I hope that I'm not, sorry. We draw a lattice path starting at the origin and a sequence of steps ending possibly anywhere, and it must remain within the first quadrant of the Cartesian plane, so it cannot go below the x-axis or to the left of the y-axis. Okay, so that's a walk in the quarter plane, and we say it's an excursion if it starts and ends at the origin, and we say that it's a meander if it starts at the origin and it ends anywhere. Okay? And this particular model of walk in the quarter plane is very famous. It's known as a Kreweras walk. And in case you haven't seen anything like this before, a fun problem, or rather an intriguing problem relating to walks in the quarter plane, or Kreweras walks, is that the enumeration is incredibly beautiful. So when you see this formula, you maybe have some ideas about how to prove that Kreweras walks or Kreweras excursions. Sorry, I might be a bit liberal with excursions versus walks. If I don't specify meander, I mean excursion. So you might have some nice ideas when you see this formula about how to prove this formula for Kreweras walks. So firstly, we could say, okay, well, this factor or term over here, this is essentially a generalized Catalan number or Fuss Catalan number. And there are many objects, you can go look them up on the OEIS, which enumerate these, which are enumerated by these numbers. My two favorites are trees and lattice paths, so ternary trees and lattice paths starting and ending on the x-axis, never going below the x-axis with this step set. So these are really simple, nice objects. Then we could perhaps say, well, what about putting coloring on some of the objects? So there are n internal vertices in this ternary tree. We could put a 4 coloring on the internal vertices. There are 2 n down steps in these paths over here. We could put a 2 coloring on these, and we get this factor 4 to the n. And then the last thing that we haven't really explained is this final factor of n plus 1. And you could imagine maybe there's some way to define some equivalence classes where there are n plus 1 elements which are all mapped to the same object. So this seems like a really nice, feasible way that you could somehow prove this enumeration, right? And the answer at the moment is wrong. So this problem has been open for 60 years, almost 60 years, and nobody has been able to find some nice, simple combinatorial proof for it. So there are combinatorial proofs, and I will discuss that soon. But essentially, the point is that things in the quarter plane are quite intriguing because sometimes there should be some really nice way of busy explaining things, and this just doesn't occur. Okay, so essentially I just quickly will give a brief history of walks in the quarter plane, or at least the study of Kreweras walks. And so they were introduced in the PhD thesis of Kreweras in 1965, where he looked at not really them as lattice paths, but rather other combinatorial objects. And then improvements on the proof were given. And things like algebraicity of the generating function were proven, and they were interpreted as lattice paths. So lots of people were busy working on trying to improve this. And ultimately, all of these approaches required some element, even if it was a small element, of busy guessing, so some sort of like little jump and then proving that it all works. And the first direct derivation was by Mireille Bousquet-Milou in 2005, where she essentially applied or adapted some multivariate kernel method, or also known as the obstinate kernel method, in order to provide a direct derivation of this formula. But if you are familiar with the kernel method, it's not really the simplest method. And shortly afterwards, Bernardi provided a bijection, but again, not to some nice, simple combinatorial objects. Well, it depends how you look at it, but decorated planar maps, which are really nice, but it's still quite an involved bijective proof, and so there's still some idea of what can be done to somehow find a simple bijective proof. And the reason that I mentioned a little bit of the history of Kreweras walks is, I know this is a little bit of an oversimplification if you know the history, but essentially the development of methods for dealing with Kreweras walks ultimately led to a rapid increase in the in research in this direction. So after the direct derivation could be done, then Mireille Bousquet-Milou and Mani Mishner then went on to classify all walks in the quarter plane with small step sets, or small steps, sorry, not small step sets. So the step set has to have one of the 8 cardinal directions, well, a subset of the 8 cardinal directions. Okay, and then after suddenly these papers appeared, there was a massive increase in the number of people working on walks in the quarter plane. 2013 is just there to get the spacing right. It's not 2013 where things massively increased. But essentially, people are still working on trying to determine methods to study walks in the quarter plane with larger step sets, classify their generating functions, that type of thing. Okay, so something that I don't think I need to necessarily explain to this community is that people like to look at patterns in combinatorial objects. So basically name a combinatorial object, and we could probably find at least one person here who has maybe worked on or knows of a pattern or some sort of thing that's been looked at in a combinatorial object. And in fact, lattice paths are no different. So people have looked at patterns in lattice paths for quite some time. And patterns in lattice paths, particularly the cases which are a little bit easier than walks in the quarter, well, maybe a lot easier, but still not easy, such as completely unrestricted walks, well, lattice paths with patterns avoided, and lattice paths in the half plane with patterns avoided. So all of these have been studied, and there are general methods that do exist in these scenarios. So the first case where patterns haven't been studied in lattice paths is walks in the quarter plane. And so since Kreweras walks are the canonical example of walks in the quarter plane and sort of the driving force behind a lot of progress on walks in the quarter plane, we can say, well, let's just see what happens. Let's take some Kreweras walks, let's take some pattern and see what comes out. So how about we take the pattern west-west? And if you count the sequence that comes out, you get this one over here. And if you look it up in the OAIS, it's a really massive surprise that this turns out to be Gessel excursions. So Gessel excursions are also extremely famous walks in the quarter plane. They've got a really nice history, which unfortunately I don't have so much time to explain. But they have a step set that's given over there. And it's sort of a miracle that Kreweras excursions that avoid this pattern are perhaps, so we haven't proved anything yet. Well, we have, but not in this talk. So it's sort of a miracle that they are related. And this is what they look like, the 11 ones of length 4, which should correspond to the uncrossed out ones over here. Okay? And so how can we prove this? Well, there are many ways you could try, which are probably incredibly difficult, but there's an incredibly nice, simple thing that you can do, and this is bijections. So bijections, we already know that in the quarter plane, bijections are not necessarily so wonderful, but in this case, it is incredibly wonderful and incredibly simple. Okay, so we have this little thing called the shortcut bijection. So it's sort of a miracle, firstly, that Kreweras walks are related to Gessel walks. And then it's even more miraculous that the bijection is incredibly simple. So we have this bijection where we say, well, we're not allowed to take a west step followed by a west step. So what can come before a west step? A northeast step can come before a west step, or else a south step can come before a west step. And if you just draw a line from the start point to the end point, and then leave the ones which are not involving west steps at all the same, you get the step set of Gessel walks. Miracle. Okay, so that's super nice. And we've had some success. So let's say, okay, well, what happens with other patterns? So again, choose another pattern. Oh, yeah? What about the length? So the length for Kreweras walks is 3n, and if you avoid the west-west patterns, it becomes 2n. But in terms of the bijection, everything works out because there will be enough of these and these to truncate it to 2n. Thank you for the question. Oh, and I didn't repeat it. What about the length of the path? Okay, so we can now avoid another pattern, and out pops Gessel walks again. So, spoiler, they're not all Gessel walks. It's not just the Kreweras walks are just Gessel walks in disguise. But this is super nice. And if we look at the ones that avoid west-west and the ones that avoid west-northeast, you can see this is not the same paths, and we can ask questions about, well, what is really going on, and can we find a bijection between these two? Because it's not immediately obvious that they are related. And the answer is yes. So what we're going to do is we're going to mark the west step, the first west step in a west-west combination. And just to point out, if we have multiple wests, we consider each pair to be a west-west combination. So we mark all of the west steps, which are the first west step in a west-west combination. And we mark all of the northeast steps, which are parts of a west-northeast combination. And then we also take what we call the local indices of this. So this just means that we look at a step's index among all of the other steps all the other steps of the same type in the path. So not in the entire path, so we count like 1, 2, 3, 4, and so on, and we take note of which ones are marked. Okay, then what we do is, in order with the marked steps, with their indices, we then take the west step and we look at its local index and we shift it before a northeast step, which has appropriately shifted local index. So in this case here, we have a west step with index 1, local index 1, and we put it before the northeast step with index 2. And then we get a new path, and we keep on doing this. We're just doing them in one step, so we ultimately end up with that. And now we've exchanged the west-west steps for west-northeast steps, and now we need to exchange the west-northeast steps, which are the marked ones, because now we have more west-northeast steps, ultimately for west-west steps. So now in this case, we go from the back to the front, so from the highest index to the lowest index. This is important because things can become shuffled. And ultimately, we then also switch it to the west step before a northeast step to before a west step. Okay, so ultimately, we can find nice bijections, and we get from this here, you can count that the number of west-wests in this one is the number of west-northeast in this one, and vice versa. And we have a bijection, a mapping between these. And we can look at various other patterns in Kreweras walks and see what happens. I will save you going through more bijections, but actually, really, really surprisingly, all of these patterns of length 2, so there are 9 patterns of length 2 that you can create from 3 steps, but then with symmetries, some are equivalent. So all of the possible patterns of length 2 end up being related to some famous walk in the quarter plane model, which is kind of insane. So here are the relationships, and here are the paths that correspond. And the question is this a coincidence? So if you take patterns of length 3, or if you take another walk model, does this also just give other things in the quarter plane? And I don't believe in mathematical coincidences, so I would say probably it's not a coincidence, but I can say that I haven't found another instance. I did not look incredibly exhaustively because this would really be very computationally hard, but this doesn't really seem to happen elsewhere. So one thing I mentioned previously that people are really interested in classifying the generating functions for walks in the quarter plane. And this is a question that's also been asked and answered for other patterns in lattice paths. And so we can ask questions about the generating functions of pattern avoidance, or what happens when you take a certain type of generating function and you avoid a pattern. So just a quick recap in case you don't know this. I don't want to assume anybody knows this stuff. But essentially a rational generating function is a polynomial divided by another polynomial. An algebraic generating function is that you have a bivariate polynomial which your generating function is a zero of. A d-finite generating function is a generating function which your generating function satisfies a linear differential equation. And then transcendental means that it's not d-finite. And there are some further classifications of these, but we're not going to get into them. But essentially, rational exists inside algebraic, which exists inside differentiably finite. And also, in case you haven't worked with this type of thing before, rational generating functions are fantastic. Algebraic generating functions are great. Differentially finite generating functions are nice. Transcendental generating functions are scary. Okay, so that's all you need to know. And so we can ask, well, in our Kreweras case, we've now drawn these connections. And in the first three cases, these are related to Gessel walks. And Gessel walks have been proved after quite a long time. They were proved that to be algebraic ending anyway. So meanders, Gessel meanders are algebraic. So all three of these are algebraic. And then the last two are d-finite. And one way that you can tell that they are d-finite, well, not that they are d-finite, but that they are not algebraic, is that you can look at their asymptotics. So if you look at how the sequence grows with n to the minus 3 factor, and there is some relatively restrictive scheme about what algebraic generating functions asymptotics can look like. Okay, and so the question is, or rather what has already been done, is that for avoiding a pattern in a completely unrestricted region, the generating function is rational. For avoiding a pattern in a half plane, the generating function is algebraic. Even for avoiding a pattern in directed lattice paths, so directed lattice path is when you always have the first coordinate is always a positive integer. Even in this case, it's algebraic, which is reasonably surprising and a recent result, perhaps even presented at FPSAC. And then the question is, well, what's happening in the quarter plane? And so we already see with Kreweras walks, which are algebraic, avoiding a pattern gives algebraic and d-finite. Okay, but does it get worse? And with walks in the quarter plane, the answer is usually yes. So here's an example of a model which is algebraic. And this model has the numbers indicate the multiplicity. So this just means we have two unique steps in this direction. And if you avoid a pattern, which you could see a pattern as just being a set of steps, a pattern of length 1 or several patterns of length 1, then you can get to this model, which is known to be transcendental. And in fact, I said you didn't need to know much more about the different types of generating functions, but in fact, this model is known to be differentially transcendental, which is the worst of the worst. So as you can see, there's quite a range that you can do with these pattern avoidance in walks in the quarter plane, and this is definitely something that needs to be looked at. So going back to, well, just to finish off and state some open problems, so we come to tell you about this dipping the toe in walks in the quarter plane, pattern avoidance in walks in the quarter plane. And this is sort of to try and get you all interested, so we have many bright minds and clever people, to get you all interested in trying to develop some theory behind walks in the pattern avoidance in walks in the quarter plane. So the first open problem is just continuation from the previous one. I would say don't try this unless you really have a lot of free time, because it's been open for 60 years. But maybe, and maybe you're super lucky, it's not necessarily likely, but if you follow some patterns in Kreweras walks, and you look at some corresponding combinatorial objects, maybe you somehow find some connection which leads to some idea for bijection. Then the thing that I mentioned about the generating functions, or the nature of the generating functions, so even just for some reasonably not so general case, but reasonably general, if you can somehow say, well, we have a generating function or a walk in the quarter plane which is algebraic and it satisfies certain properties, then if we avoid a certain type of pattern, it will give us this type of generating function. Some results in this direction would be fantastic to sort of get things going, although I imagine they could be incredibly hard. And then lastly, so if you want to know a little bit more, so I didn't go into the kernel method during this talk because there's limited time, and also, yeah, but if you look at the extended abstract, we discuss a little bit about why the kernel method, so up until now, kernel method has been sort of like a very strong tool that people can use to try and push forward in walks in the quarter plane. And we discuss why this fails in the case of patterns. And to quickly summarize, you essentially have more unknowns than you are able to solve for. But if you find some walk that is quite symmetric and you can have some cancellations in terms of the unknowns, perhaps then you have enough information to somehow get some solution. And even just a step in this direction would be fantastic. So thank you very much for your time.
Thanks very much. There'll be a brief presentation right after the question session, so don't rush out. But any questions for the speaker right now? Nathan.
The walks in your main walk seem to be, the steps seem to be type A2 groups. Did you ever try to do sort of a type B2 version of this?
No. Oh, yes, repeat the question. So the walks seem to be type A2. Would it be possible to look at it B2? Yeah. Well, I'll admit I don't have much background in algebraic combinatorics. So no, I don't know the answer, and I haven't really looked at anything like this. But yeah, it could be interesting.
Colin.
Yes.
Repeat the question.
Oh, thank you. So the question was that the formula for Kreweras walks without pattern avoidance are relating to, well, it's a power of 2 times by the formula for 2-stack sortable permutations. Yes, so there are quite a number of objects if you sort of just drop one term or add in the factor of 2 to the n or whatever. And we did think about busy looking at 2-stack sortable permutations. So at one point we were sort of like a little bit crazily looking at what could be done also there. And yeah, that was something that we considered, but I don't know if anything came out of it, but that doesn't mean that nothing can come out of it. It's possible that it's just, yeah.
Yannick?
I guess this is a 2-dimensional case for the Kreweras walk. I guess we could even consider this 3-dimensional, 4-dimensional, where the walk for all all ones and for negative ones in one direction. So are there results regarding to these higher dimensional generalizations?
I'm not entirely sure.
Question?
I think, oh, sorry. So the question was that the walks, these are 2-dimensional walks, and what would happen if you looked at like higher dimensions, like 3-dimensional, where you have a unit step in each direction plus a longer diagonal. The answer is I'm not sure, so I think this would be very hard. At one point, so Kreweras walks are actually from a generalization of the ballot problem, where you now have 3 candidates and 1 candidate must always lead, and then the other 2 candidates must always be behind. And if you look at the generalization of that, for example, the answer is that it's transcendental, we believe. So we looked into this, and it's transcendental, and then trying to do nice things, as I mentioned, is not always great. But yeah.
There's another answer from the front row.
Kreweras and Jacek have started to look into this, and
Okay.
the situation is quite incomplete, but they have several results on that.
Okay. Thank you.
The actual voice of Krathenthaler. Yeah, go ahead.
Yeah, so I saw you had some asymptotics for the number of pattern avoiding Kreweras logs. Do you know anything about, like, if you're avoiding, let's say, a single pattern, does the, I guess, exponential growth rate always exist? Does that question make sense?
Well, this is something that we were planning. Sorry, I've been really awful at repeating the question. The question is that we have some asymptotics, and essentially what can I say about asymptotics? This is something that we plan to look into for the extended version, and also look into different things like the drift of the walk, because as the pattern gets removed, this can change things and get asymptotic results in that regard, yeah. Because I think at the moment, this is.
Do you have a question?
So, are meanders in any way easier to count than excursions? And can you break up excursions into meanders and then sum them up together?
So the question was, I got it this time. The question was, meanders in any way easier than excursions? And can you somehow break meanders up into excursions? Or excursions into meanders? And the answer is no. So many of these results, the answer to are meanders easier than excursions is no, first part. And the thing is that in cases like the very, very simple bijection between Kreweras and Gessel, you suddenly are having sometimes 2 steps going to 1 step, and then other times 1 step going to. That doesn't mean there aren't things which may be like another bijection which doesn't handle that, but I doubt really that would be possible. And also for meanders, you would need to have, I think you would need to use much more powerful tools for meanders to try and get at least enumerative results out. In terms of breaking up excursions into meanders, we did look at this at one point to try to find some sort of factorization, but I think no. So Kreweras walks are algebraic, for example, but they aren't context-free, which means that you can't expect to find some nice decomposition of generating functions like you might do for like a binary tree you recursively decompose. So you can't necessarily find one like that. And so something like decomposing in excursions into meanders or meanders into excursions, or whichever way around, I think poses a little bit of difficulty. But we have looked at that, and we were trying to somehow do some factorization in some sense.
See, we're running short on time, but I saw Travis, did you have a question? No. Oh, Ben.
Have you looked at all when you're potentially avoiding multiple patterns?
Yes, so avoiding multiple patterns, at least in, for example, patterns of length 2 and so on, nothing really comes out. And you are very restricted in this because without the presence of powerful tools, so perhaps you could sit with generating functions and bash something out after extreme pain and really a lot of time. But at this point, we are reasonably restricted with pattern avoidance to actually looking in the OEIS and so on. And then generating sequences which are long enough to use something like GFUN or even just perform any sort of guessing is also incredibly hard. So I think 6, 7, 8 terms is probably the maximum that you could go, but I speak completely under correction as not a computational specialist. But me and one of my co-authors had a competition to see who could generate more terms faster, and the answer was we could generate the same number of terms, and that was 6 within like a very reasonable amount of time. Yeah. So unfortunately, yeah, the more powerful methods don't really exist.
And Mike?
I noticed that one of those sequences, I think like diagonal excursion was the Catalan number squared.
Yeah.
And I saw that like, so even though the Catalan iterating function is algebraic, like when you square the coefficients, it's not algebraic. Is that typical if you have like an algebraic dimensional?
I think it's, yes, question, thank you. So the question was that one of the terms, and I think it's close enough that I could get to it. Here. Yeah. That's essentially these polio walks, which now I removed which one is corresponding to, but I think it's this. Okay. That it's Catalan numbers. Well, I think one of them is Catalan number n times by Catalan number n plus 1, the other one's Catalan number squared. And I think, I'm not sure about the answer, but for sure things like Catalan numbers have asymptotics, which when you square them, you get a negative integer. And if you square something and you get, well, if you get a negative integer, it's not going to be algebraic. So for sure, probably there are some examples of algebraic functions when squared, which get algebraic functions again. But this, for example, via this fact that its asymptotics don't fit, is not going to be algebraic.
I think we'll have to hold other questions till the lunch period, otherwise we'll use it all up. But let's thank the speaker again. And please hold your seats for just a minute. There's a brief announcement from Greta.
Hello. So we wanted to advertise a program happening in the spring 2024, not too far from here, at IPAM. This is the Institute of Pure and Applied Mathematics, which is at UCLA, right next to the math department. The program name is Geometry, Statistical Mechanics, and Integrability. You may not see combinatorics or algebra in the title, but I promise you there are some things that may be familiar. So here is a plane partition, lozenge tiling, cylindric plane partition. So it actually may be relevant. Here I'm one of the core organizers of the long program. And here are some. Okay, I guess we need to log in on the internet. It's a limit shape, actually, that looks like a giraffe. That's why that's the all right. Okay, so here are the activities associated to the program. Of course, you can apply. The deadline is until October if you want to be there for the whole program. There are still some space. There is a little bit of space left, but you can also come just for some workshops. And of course, I can recommend this workshop here, Integrability and Algebraic Combinatorics, in April, which is co-organized by Alejandro Morales and myself and Vadim Gorin. And there you will study more pictures like this, like Lozenstein. So that's all I wanted to say. I don't know. Yeah. So yeah, please apply.